I'm a bachelor student at the Hochschule Kaiserslautern. I'm studying automation technology. So this was my thesis. I did for 3 months. So basically it's a simple project actually, because the title itself is detection of driver drowsiness by calculating the speed of the eye blinking. But this project is really practical in real life because, as you know, many car accidents were caused by drowsiness, and maybe because of stress at work, long distance driving, and etc. So there were a lot of researchers about this topic to detect drowsiness. But however, for example, they tried to calculate the number of pixels of the iris, cornea, etc. However, this researcher is a bit it is a problem with this research because they able to detect drowsiness after the driver already fall into microsleep. So microsleep is a sudden temporary sleep that may happen only for several seconds, 2 or 3 seconds, but for these 3 seconds it's really crucial for a driver that may happen a fatal accident. So our proposal is to calculate the speed of the eye blinking, because as you know, one of the characteristics of a sleepy person is a slow movement of the eyelid. So for the eye detection, we use the HOG and SVM approach. And then the most important variable is the eye aspect ratio. So the eye aspect ratio is based on the landmarks. As you can see on the picture, we have 6 points of landmarks. So these landmarks will be recorded from each frame, and then it will be extracted and inserted into the formula. So ear or eye aspect ratio, ear is the short form for eye aspect ratio. And then for this graph, it's to show that the behavior of the eye aspect ratio. It depends on the state of the eye. For example, if the eye is opened, then the value will be only above 0.35. So when it closes, the value drops drastically until 0.13. But this value depends on the size of the person's eyes. So the other important variables is the average eye size, which will be derived from the ear or the eye aspect ratio. And then we have the maximum and minimum threshold. So as you can see, the maximum threshold is the above one and the minimum is the below one. So we also have another variable, which is maximum and minimum ear. So this max and min ear, max will be calculated above the max threshold, and min will be calculated below the min threshold. And the last one is the time, the start and stop. So the basic speed formula is distance over time. So we replace the distance as the maximum ear and minimum ear. So this is an overview of our algorithm. First, the algorithm will find the size of the driver. Next, the thresholds, and then the max eye aspect ratio, and then the time will start. After that, you will find the minimum ear, the time will stop, and then you will calculate the speed. So if the speed is below the threshold, then an alarm will be triggered. It will notify the driver that he or she is sleepy. So we've conducted several evaluations and tests to test the robustness and the reliability of the system, which will be tested on different people with different ethnicity backgrounds and also genders, because different people have different eye size. So the first evaluation is for constant ear or eye aspect ratio value with different distances, and the second one is the evaluation to differentiate the speed between normal and sleepy blinking. So the last one is the evaluation for different head positions. So the first one. As you know that when a driver moves forward or backwards, the eyes change relatively like different from the camera perspective. So this evaluation is to prove that the eye aspect ratio doesn't change. Doesn't change the same as the distance between the eye and camera. So for the method, we use 2 images instead of live stream video because the image has a static object. So then we will have a fixed value as reference. So for the first, for this evaluation, we have 2 approaches. The first one, we are using the distance between P2 and P6. You can see on the image with the eye, there's 6 landmarks. And then the second approach is by using the eye aspect ratio itself. So for the first approach, you can see that we have 2 images. The first one is the near image, which represents the eyes are near to the camera. And the second one is the far, which eyes are far from the camera. And then for the near image, we have the distance. The distance is 8 pixels, and for the far image is 4 pixels. This means that the value changes if the camera and the driver, the distance between them varies. And this is the second approach where we use the eye aspect ratio. So for the near image, it has 0.31, and then for the far image is 0.3. So which is the deviation is only 1.5%. So this proves that the eye aspect ratio value is reliable and we can use it in this experiment. So the next evaluation is about the normal blinking. So this is the graph. The blue line is the eye aspect ratio values. The gray line is the maximum threshold. The orange line is the minimum threshold. So the maximum ear and minimum ear was selected correctly, and then the speed is calculated as 3.8 pixels per second. So 5 blinkings were recorded from each participant, and then on the right side, the graph shows the speed of the eye blinking from a person. So most of the speed are above 1 pixel per second, and the average is 2.04 pixels per second. And for the sleepy blinking, you can see that there are more values below the orange line or the minimum threshold. This indicates that the person closes the eyes longer than usual. And then the values for sleepy blinking is only between 0.52 and 0.22 pixels per second, and the average is 0.36. And the last evaluation is for different position head movements. So for the downwards and upwards movement, they share the same result, which is the algorithm is able to detect the eyes up to a certain degree and also able to detect the eye blinking. However, the ear becomes smaller, which it will affect the speed calculation. And on the right side, when the head turns to right or left, the algorithm is able to detect the eyes as long as the eyes is visible to the camera. But the speed is inaccurate, and some speeds cannot be calculated from certain angles. And for the conclusion, we are able to distinguish between a wakeful and drowsy blink of a driver in real time. However, there are several problems that we face during the test. So the first problem is the algorithm cannot detect the eyes in a certain angle and a certain head position, as the previous slide. So we suggested that we need to identify, the algorithm needs to identify the rotation of the head, and also includes additional camera position in different angles. So the second problem is the facial expression. For example, smiling. When someone smiles, the eyes become smaller. So it will impact the eye aspect ratio and also the speed calculation. And so the suggestion is to add new algorithm to detect the facial expression and also to adapt new and updated maximum and minimum thresholds. So lastly, the problem is the inclusion of optical effects that can occur due to eyeglasses. And yeah, this is without the solution. Thank you.